afternoon. My name is David Sandino. I'm the director of the Global Risk Research Community. This is wonderful to see this many people to come out for a talk on infrastructure. What the world needs is a lot more attention to people who want to talk about infrastructure. And today we have two wonderful colleagues from the UK, from Cambridge. We have Paul Larcey and McShane, and we're hoping the beginning of a beautiful friendship. We're here to listen to these guys, but also to continue talking and start building this network of folks who are interested in risk, et cetera, and apocalyptic concerns to cheer us all on. So with that, thank you very much for coming, and we look forward to this.
Great. Well, thank you very much for the introduction, and thank you for the invitation to come and talk, and your very kind hospitality while we've been here. Thea's been taking us on a tour of Princeton this afternoon, and we've really appreciated seeing what a beautiful campus you have here. Actually, it's one of the few places that's probably more Gothic than Cambridge, where we come from. So we feel very much at home here at Princeton. So my name's McShane. I'm a university lecturer at the Department of Engineering. My background is in mechanical engineering, and Paul Larcey here. I guess Paul will introduce himself in a moment. And what we're coming to present here is the start of a new initiative really at Cambridge, which is looking at issues related to infrastructure, risk and resilience. And it seems to overlap a lot with what you guys are interested in. So this is a fantastic opportunity for us to present our ideas on this topic really, and engage with your group and get your thoughts on what we're working on here. So I'll start by just giving you a bit of an overview of what we're going to talk about today. So in a moment, I'm going to hand over to Paul to talk about what we mean by infrastructure and why we think it's important to increase resilience in infrastructure problems. And also our thoughts on a multidisciplinary research approach that's needed to tackle these kind of problems. So we're from an engineering department, so we tend to think about the technological aspects of resilience, but what we're increasingly becoming aware of is the importance of other aspects like risk analysis and perception, the financial aspects of resilience, and also the political side of resilience and infrastructure as well. So we're very interested in broadening out into a multidisciplinary approach to research, and we're going to talk a bit about that. And then we're going to end with a couple of case studies, really, which Paul and I will present that are sort of focused on our areas. So Paul will give a case study on infrastructure finance, construction finance. And as I said, my background is in mechanical engineering. I'm going to talk about advanced materials and design methods in resilience engineering. But before we get stuck into that, I just wanted to give you a couple of slides to tell you a bit about our department. It's quite an unusual engineering department, the Cambridge department. We are a big department. We are the largest department in the university. We make up 10% of the university on our own. And we're unusual in being a multidisciplinary department. So we don't have a mechanical engineering department and a civil engineering department. We have one department in one building, broadly speaking, and we span all ranges of engineering. So we divided up into these divisions, which are creatively named A to F. And A is fluid mechanics and thermodynamics, and we've got electrical. This is me, so I'm in mechanics, materials and design. This is division C, a very catchy title. D is civil and structural. We've got manufacturing management and information. And we bring all this together in one department. So we are used to multidisciplinary approaches to things. It's been highly successful, this approach. Our engineering department is one of the most successful in the UK in terms of our research impact. So we think it's a model that works rather well. And linked into this, we have a number of strategic research themes which are designed to bridge these departments, these divisions, and some of them are relevant to what we're going to talk about today. So the first one is energy transport and urban infrastructure. So this is looking at issues related to sustainability in an urban environment. And then the second one is uncertainty, risk and resilience. So at the moment, activity in this area is focusing a lot on mathematical modelling of uncertainty and risk. But we feel that this is an area that our new research initiative could contribute to. And then we've got the third one, which is a growing area in engineering, which is looking at the life sciences and healthcare, recognising the ageing population and ways of solving that. And then finally, a cross-disciplinary initiative looking at how to link up better with industry, so how to inspire new research ideas by linking up with industry. And again, this is something that I think we can bring to with this initiative. So, as I say, we're starting this new research group really looking at the problems of infrastructure, finance, risk and resilience. And we're not starting from scratch in our department. We're building on a number of very large centres that work in this area. So there's a very big one here called CSIC, which is looking at smart infrastructure and construction. This is headed by Professor Robert Mayer, who's the Master of Jesus College. And this is really looking at instrumenting buildings and infrastructure to try and gather data about how things respond during their entire lifetime. Then we've got the Laing O'Rourke Centre, which was founded recently by a large endowment from Laing O'Rourke, who's the founder of this civil engineering and construction company. And that's looking at aspects of construction technology, sustainability issues, and it runs its own master's program as well. So what we're having to do is really draw on all of these different areas and focus them on this issue of risk and resilience in infrastructure. But in addition to that, we're building on links from outside of the department. So we've got links with the Judge Business School, the Centre for Science and Policy, which aims to link up engineers and scientists with policymakers. So they run a series of meetings and forums for discussing these kind of issues. And also the Institute for Sustainable Leadership, which focuses a lot on executive education in the area of sustainability, but they're interested in getting more into research. So we're hoping to draw on these external groups as well. And to just give you one example that's relevant to your group here is the risk group, the Centre for Risk Studies at the Judge Business School. So this is headed by Professor Danny Ralph. And so they're very interested in some of the areas that also overlap with what we were talking about. So this is an extract from one of their recent white papers on a taxonomy of threats, so looking at the range of possible risk factors and how they're interdependent on each other. So they've built up this matrix of different risks and how they link into each other. And at the moment, their research is focused on a sort of rather top level. And what we're hoping is to engage with this group and bring in some engineering and technology into it as well, so it can drill down into some of these risk elements and bring in a sort of an engineering and a technological perspective on it as well.
How many people are associated with the activities we're talking about? Hundreds?
These centres are rather large, so it tends to be quite fluid because many of these centres have a number of collaborating academics. So CSIC might have maybe 15 to 20 academics and maybe a similar number of collaborating companies. So it's a rather large activity. This maybe
CSIC is multidisciplinary, so it's got people from physics.
Yeah.
Yes,
No,
I understand that, but
the size, yeah.
Yeah, it is quite big, and then Laing O'Rourke Centre, maybe 4 or 5 academics, and Centre for Doctoral Training, same again, and similar here with Cambridge Centre for Micromechanics, so it's that kind of scale. I'm not so sure about the risk group.
They've got about 10 or 12,
yeah,
and then they're building up doctoral research.
Yeah, so these are reasonably large activities. So what I'm going to do is I'll hand over to Paul now to tell you a little bit about our thoughts on infrastructure resilience and the multidisciplinary approach.
Yeah.
So there's the
Was the
yeah, that'll be fair.
Hi. So my background is engineering at university, a little bit of engineering afterwards, and then straight into management and finance. I've had enough of that now, so I'm going back to an academic world, and I helped sort of put this together with Graham, and we realised that actually there is an interest. There's this whole area of risk, resilience. Resilience can mean many things. It can mean social resilience, engineering resilience, but the whole area is sort of ripe for academic study. And Graham spoke about a guy called Danny Ralph at the risk group. And he's a very, very well-known risk guy, again, operational research, a lot on finance, and he read the first sort of proposal we put together, and he was meant to have read it like 2 weeks before, and he turns up like 20 minutes late to a meeting. Obviously, he'd just read it, and he said, actually, this is really good. And that was the first start that, yeah, there's something, there's something there. You know, the UK government are interested in looking at the work we're doing, the EU, and you can see that research from the World Bank, UN. It's a really, really interesting subject. It's all slightly nebulous at the moment, and it needs a sort of little bit of centres of gravity to pull in the subjects, otherwise it's too broad. So I'll talk a little bit about how we see this going forward. But first of all, what is infrastructure? So infrastructure as a term actually came from the military many, many years ago, but now we see it as this. Sometimes you've got to be a little bit careful when you read reports, sometimes people miss out some of these areas. So often housing here is missed out, and governments particularly like to leave out the housing element because that's mostly private sector. It's a little bit contentious, and it means they're not being held to any sort of any promises that they've made. But we decided to include it in at this stage. So it's exactly what you'd expect from global infrastructure, environment, transport, energy, telecoms, civil and so forth. A pretty wordy slide, sorry about that. We want to bring in the idea of resilience and also the growing problem of interdependency of systems. So Graham spoke about Professor Robert Mayer, who's the world expert in tunnelling. And if you want a tunnel built, you speak to Robert. And what he's doing in his centre is putting all the data systems together. So different wireless protocols, different sensors embedding, fantastic stuff, collecting all this information. Human agency is removed from the actual operation, which of course sounds fantastic until something goes wrong. And they're not actually looking at that aspect. They're just looking at the technology and the exploitation of technology. But there's an increasing problem of interdependency. And some of you may be aware of some of these guys down here who've spoken about it. Again, in slightly sort of wider terms, because we're not quite understanding what the problems might be, but there's a growing academic consensus of some of the issues. Now, one of the problems that I have found when I was doing large-scale project financing is that people are very concerned about the robustness of what they're investing in. And as you get to more interdependency, more technology away from human agency, people say, well, exactly how robust is my system that I'm putting several billion into? So it's getting an increasing problem from the people that are funding. What we're looking to do here in the group is, I think you've just seen this slide, showing the three sort of pillars, risk analysis, resilience engineering, and social policy. It's these overlaps. Graham's got a lot of research down here. I've done some research up here. People nicely sitting in their little silos. It's the overlaps that are interesting, and especially to try and get there in the centre, where we actually get deliverables. Cambridge, obviously the thing that we do most of all is 5-star, 4-star research. That's the goal. But actually, I'm interested in actually getting things, real-world deliverables, things that will make a difference, on top of the academic research, obviously. Why this group? We're not building enough infrastructure globally. Miguel just said, there's just not enough. We've got a growing demographic issue across the world. I'll show you a map in a second, with environmental pressures increasing. There's more than enough money out there. There's several hundred trillion floating around the world. And we'll come on to one of the issues why it's not going into infrastructure. The funding landscape has changed. Again, we'll touch on that after the banking crisis. Increasing reserve over the resilience and interdependency, as I just spoke about. And what we feel is that many areas intersect these issues, but they're all examined in isolation. If you do a literature search, which I did 2 years ago, some great stuff, but it's all not quite joining the dots yet. So there's a global shortfall, and every year it increases. 2.6 trillion is missing. How do you get to that number? Well, you look at the global demographic increase, you look at increasing urbanization, and you come up with a relatively simple arithmetic calculation. This is from OECD, and it's a McKinsey report as well, so you can see the shortfall there. There are some notable exceptions where that's not the case, but overall there's this gap increasing every year. Now, there's $300 trillion by 2020 that will be floating around the world, and it will be floating around the world handled by our friends in the city and Wall Street, and they'll be looking for how they can get double-digit returns, and they'll be looking for liquidity, so can they get their money in, out again very quickly. Infrastructure is not an asset class they particularly like. But the money is there, and the problem is there. How do we get them to join together? So I'm sure you've all seen this. This is demographic rates of growth. We see Africa, we see parts of South America. These are going to be problems. Thea was showing us one of those NASA maps of the world, which I'm sure we've all seen, where you look at Africa and it's completely dark at night, with a few sort of highlights. There's not enough infrastructure there for the massive growth of population, especially as the majority of them are now urban, and that's going to increase going forward. The World Bank say that global building stock is to double by 2050. So there is momentum there, but is it the right type? And is it being put in terms of dependency and resilience going forward into the future? I think we probably all know these statistics. I think it's to read them out. You know, there's a lot of issues in the developing economies where people haven't got access to basic infrastructure needs. And I think one of the interesting areas down here, it's holding back private business development. So in sub-Saharan Africa, 10% of any business cost goes into energy. In China, it's 3%. And it's actually a little bit less here in the US and Western Europe. So just to have the energy to run a business, i.e. have the lights on, to have a computer working, a lot of it's taken up already. So improving infrastructure also lifts up a country's economy. Short run, it can create jobs. In the longer run, it enhances productivity, increases private capital formation, which is spoken about. It also has a significant effect on health and education outcomes. And the statistics are there to prove that. And I think we can see down here, I've used one example. All-weather roads in Morocco increased school attendance by girls 28%, 68%, between 85 and 95, as the improvements in road safety through more women's time. They also improved health indicators, the number of visited hospitals and health centres has doubled. It's getting those routes, how people can get to places and get the experts to come to them. Graham said we do a little bit of work now with the Cambridge Centre for Sustainable Leadership. They are talking about infrastructure in terms of supply chains for food and water. Well, that's great, but you have to have the physical assets there. They actually have to be in place. Everybody knows it's a problem. This was in The Economist recently, $1 trillion gap, and this chap, I think, does something in a college a bit further north from here. And that was in the FT, saying why investment in infrastructure actually is good for the economy. This is some quotes, I won't read them out, from Kim Yong-kim, who's the World Bank president, and they've just opened up a new infrastructure facility, which is there to bring together and look at some of the issues we're talking about. So, but why is it not happening? Why are we not seeing the investment that we should do? Because there's a gap. Why are people not putting funds into it? Well, the financial crisis of 2008-9 has created a more risk-adverse landscape. Infrastructure, especially in developing economies, is perceived as a very, very high risk. And so therefore, I'm sure we're all familiar with the way that debt is pushed out, and if it's a higher rated debt, you're going to pay more for it. Conversely, as I said, 300 trillion, more liquidity exists globally looking for those higher returns floating around the world. If it doesn't go into projects of social utility, it's going to go into ludicrous commodity booms or just ridiculous scams like we see in London at the moment, where suddenly properties are 150 million at the top end, where people don't even live in them. So it's much better to put it into a dam than it is in a flat in London that you don't even live in. So how are we going to do that? What's been the problem driving this? Well, after the crash of 2008-9, is everybody familiar with the Bank of International Settlement? Yeah. So based in Switzerland, regulating the world's banks. What they've said the banks have to do is to improve their equity base and limit their total assets relative to that base. Basically, less lending. So infrastructure has been put alongside property development, and if you want to invest as a bank in infrastructure, you have to have, for every billion, you have to have the billion in reserves. So that's put a lot of pressure on the project finance teams in banks. And banks will very quickly move away from project finance because it's not making anything for them in terms of returns. So although there's a well-established project finance sector, it will start to decline. And people joining the banks, I don't want to go in that, it's just going one way. So that's going to be a problem. We'll come back to that momentarily. There's also something called Solvency II, which is really digging into the interesting side of EU legislation. And this, again, is all about making sure insurance companies have enough of an asset base. So AIG went seriously down the toilet when the crash happened. This is trying to resolve that issue. Again, taking a harder look at any projects. Instead of just writing off or doing multiple options on a project, they're going to really dig down a little bit further. They're both being slowly implemented, these things are. They're going to be in place by 2018. So there's going to be less money, tougher rules, and more due diligence of potential investments, which in itself is not a bad thing, but banking being banking, it's just going to turn away from it completely. So the perception of risk and appetite has changed. There's also less money from governments. You know, if you go back over history, you will see the large amounts that governments have piled into their own economies. This has now changed. We're seeing increases down here, but look, compared to where they were. There's a problem of global austerity within governments. You know, governments are not allowed to borrow, they're not going to be borrowing as much as they used to. So a lot of the funding from infrastructure is going to have to come from the private sector. But the problem is the private sector has now got these new rules on it that make it harder to go to put that money into it, and at the same time, it's something they didn't quite like anyway. So we're getting these sort of double whammies. Now, Basel III is to stop our friends in the banking world doing casino banking. But the unfortunate knock-on effect, which they didn't quite think about, is the effect on project financing. Unintended consequences. But there is a light at the end of the tunnel. Government constraints, not so much government money anymore. Banks may no longer be able to support the life of a project, but they still have an appetite for funding the construction phase. The construction phase of any of these projects is the most risky because you've dug a hole in the ground, you've filled half of it with concrete, and if you go bust, who gets their money back? If suddenly your funders say, actually, we want to put our funds somewhere else, you can't. We haven't finished it yet. So that usually attracts very, very high. Everyone's familiar with Moody's and Standard & Poor's, I'm sure. If you look at Moody's ratings, you get like a CC, BBC for this. So really, really sort of high risky assets. Once you're past that into the operating phase, you're into up to AA's or even AAA's because things finished, the major capital has been spent, and you're getting a return. But how do we get through this initial thing? Now, new funding is going to be required for this operational phase, the bit where you actually get some money back when you're supplying water or electricity. And there are some people who have got funds, so pension funds. I'm actually working with the Canada Investment Pension Board at the moment, and they're very enlightened people in Canada. And they're actually investing for 25, 30 years. They've just done a project on toll roads in Chile. But they're quite unusual. The pension funds tend to be guys who are investing just in equities, and again, they're looking for minimizing risk. Sovereign wealth funds. Wow. There's a lot of money in China, there's a lot of money in the Middle East, in the UAE, and we're seeing some of them now coming into infrastructure projects. In the UK, we've got China helping us build our next set of nuclear power stations, at quite a price, I must say. The Qatari Sovereign Wealth Fund is helping to build a super sewer system under London, and I can't remember who's helping us build HS2, but there's a new high-speed train system going through the UK as well. That's another Middle Eastern Sovereign Wealth Fund. That's great. Going into the UK, we've got quite a good credit rating. We'll put money into that, but not necessarily into Nigeria or Kenya or parts of the world that actually probably need just a road rather than the ability to get to Manchester 30 minutes quicker. Hedge funds, they do dabble a bit, but you touch them very warily. And the bond market as well. You can actually get a bond going for the construction phase and the operational phase, which has been useful in the past, and I think will come back again into the future. But again, their risk appetite has also increased. These investors don't usually have the skill, and possibly not the appetite for such investments. That's the problem. So the project finance banks, a lot of these guys have worked in it for a very long time. They understand the risks. They understand the risks of the country they're going into. They sort of understand the risk of the technology and the engineering, but we'll come back to that. But these guys, they're not really into this. So we're going to have a conversation with them to say, look, this is an area you need to be in. This is just something we knocked together, which gives us a sort of idea. I worked in management consultancy for a bit. I apologise about So a matrix always has to be somewhere. If we look at infrastructure spend going up, social instability going down here, we've got some areas of the world, Northern Europe, I don't include the UK in that, by the way, Canada, Australia, New Zealand, Singapore, Hong Kong, quite sophisticated planning, long-term construction programs. They really are planning well. I would say the US and the UK are probably more down here, where the road network in the US, I'm sure you're all very familiar with it, and I do believe that 60 to 70% of all your bridges would fail the European Union safety test. There are problems even in developed countries. But the one I really want to look at is down here, the growing populations, the massive demographic growth. These are the guys that if we don't find a mechanism to help them build their infrastructure up, there will be political tensions, and also you are not utilising the strength of their people, the capital of their people, their minds. You're not allowing them to be part of our modern and sophisticated economy. And we can't just seal them off. It's going to be a massive problem for all of us. We have to think how we get a mechanism to get these funds and this engineering into these parts of the world, and in a different way than has been in the past, where basically we've been funding the political elite who give 10% to the project, and the rest ends up in Zurich or London or New York. This is quite, again, very wordy. These are just some of the startup projects we're thinking of doing in the centre. So group, I'd say centre, you need 10 million to be a centre, not that to be a centre for a group. So complex adaptive systems. Can infrastructure be a complex adaptive system? Actually, there's a lot of work saying no, it can't. It is too complex, it's too big. So that's one of the areas we want to look at. Interdependency, again, we've spoken about that. Insurance modelling, we've got the UK actuarial profession. They're a little bit sort of, I think they're seeing that possibly the world of just looking at mortality tables is not going to keep them going for the next 20 years. They're looking at taking those mathematical modelling skills into new areas. So we're working on them, again, in a very interesting area of using mathematical modelling, but also behavioural research. Not just sticking at those models, actually talking to real people. Some new funding analysis. We're working with hoping to work with the UK Treasury Infrastructure team to look at new accounting methodology. I don't know if anybody's familiar with long-term finance, confidence accounting. It's rather than just looking at it as the standard accountants, that's the hurdle rate, you've passed it, fine. It's saying, well, what is the future projections? What are we going to use this for? That's a big challenge. Funnily enough, the Treasury is the most important department state in the country, and they like to do things their own way. So that's actually a big challenge. And physical resilience, and Graham will talk a little bit about that. Because if we can't make things physically resilient to usage, to malevolent attack, and a lot of the parts of the world we're looking at do require this, whether we like it or not, they do require it. And also the problems to do with climate change, and which we're not going to talk about climate change here, by the way, and just the problems of coastal cities and so forth. Right, so this is mine. This was a small research project, about 9 months to a year. The relationship between all elements of the infrastructure supply chain, what's happened post-2008, how's risk perception altered, understanding the new regulatory frameworks, and does the contracting sector have adequate voice in terms of mitigating risk perception in engineering, project management, efficiency gains, and use of technology. There's been massive changes in technology and engineering within construction. You've got to the point now, construction engineering can almost be like building an aeroplane. People don't think that. They see a building site, they see guys wandering around, it looks a bit chaotic, but actually the engineering and technology has become extremely, extremely efficient. And that is not getting into the guys who mark the risk for the construction phase of these projects. This is how risk looks in terms of infrastructure projects. You have the building and development, very, very high risk. The construction period, obviously high risk when you start. People start to see it being built, fine. Then you have the ramp up, and then once you get into operation, this can go on for 50 years down here. Actually, the risk gets very low. So that's what we have to do, is try and bring this down. And this is quite hard. This is going to take the modelling, but this this we can bring down by the engineering, the technology. You know, if we can get it down to here, we just make the thing look more attractive to investors. So this is the research we did. Spoke to about 20 very senior players in contractors. So contractors are people like over here, it'd be Bechtel. In Europe, it'd be Vinci or Wade. Big global contractors, the guys who build these massive big projects. Spoke to them. We spoke to bankers. We spoke to the insurance sector and others who were sort of interested in the field. About a two-hour session, series of interviews, about 15, 20 interviews. We then used concept mapping. Everybody familiar with concept mapping? Yeah. What we want to do next, this project is going to move on and we will start applying some Bayesian network analysis to it. So we'll start looking at hypotheses, inference, and start to try and get more of a quantitative feel. But at the moment, what we've got is the interviews and the concept mapping. What we found is that there is a disconnection between the clients and the sponsors, the people who start the project off, and the contractors, the people who build it. And you can see down here, this I think went through TiVo software to show that the conversation's all going up here. The contractors don't actually talk to anybody, because it's all this conversation goes on up here. What do we want? How are we going to fund it? Here's the funding stream. And then it's like, let's find a contractor, which they just put out to tender. So the contractors don't actually get to talk to the people who are saying, well, what's the risk element of this? So they're not part of this conversation. What we found was a loop, which is in concept mapping, it's where people really are sort of reinforcing and talking to each other in separation to the whole group. And this is the, sorry about the colour, it came out from the program. This really is one group talking to each other, and it's the modelling side and the finance side. And our feeling is it's reinforcing the perception of higher risk, because they're just talking to each other all the time. And they're using modelling companies, modelling firms, where they're just talking up the risk. So the potential, the new regulations coming in, the Basel III, the Solvency II, will increase this, causing new investors to reject projects or price very, very aggressively. I said that you've seen some successful projects in the UK and across Europe with sovereign wealth funds. That's true. They've given the money, but at a very, very high price. A very high price. And that's in the developed world, let alone developing economies. These are all the players who are involved in this. So the investors down here, you've got some global regulators, but these are all the guys involved. So you've got global contractors who've built these multi-billion pound projects. You've got insurers and reinsurers. You've got modelling firms, and academic is meant to be over there, because modelling firms offer spin-offs from academic finance departments. You've got investors, you've got the rating agencies, the Standard & Poor's, the Moody's, and you've got some intermediate services. But the big areas are here. These are the guys who determine what the actual risk is. And the rating agencies, so that again, it's Moody's and Standard & Poor's, Fitch, they have a project finance methodology. They now acknowledge that it's not actually robust enough. Now, but these are the guys who will give you how much it's going to cost to pay for your project. Now, they got it really right, did they not, in the crisis? You know, they were on the money, spotting all those banks not doing things correctly. But they're still here, and they know that's a problem. So we're hoping to do some work with them on that. Tentative conclusions, there's an appetite for new entrants. Pension funds and other alternative funds, they want to be involved. But what do we do to raise the attraction of project financing and infrastructure as an asset class? Well, we start a dialogue using a common risk language. We bring in every part of the supply chain. Demonstrate that risks of construction phase are lower than currently priced in, and operating risk pricing reduced by increased asset resilience. Because if you dig into some of the projects that have got funding, people are very concerned about, I've put 10 billion into this, what happens if, we're going to talk a little bit later about Fukushima, what happens if a catastrophe occurs like that. And I put this one in bold because it's this policy challenge, it's a global challenge, aligning those global investment funds that are out there and global governments to get that spending into projects that create social utility. We don't need another housing subprime boom in the States or in the UK. We need this money to go into things that's going to produce social utility and actually change people's lives for the better. Great. So Graham's going to talk to you about the engineering challenges of this.
Okay, so we've heard a little bit about the finance side. So my background is in materials engineering. So I'm going to give you a brief overview of how I think research in materials engineering might be able to contribute to this issue of resilient infrastructure. So this is a nice sort of introduction to advanced materials, which I've stolen from Professor Mike Ashby, which shows that really in the last 100 years we've seen an explosion in the variety and complexity of engineering materials. And so if we go back in time, we have a very limited range of materials, and this really takes off. But actually, this isn't evenly balanced across the sectors. So in defence and aerospace, they're really exploiting this whole variety of the material spectrum. But in construction, it's more conservative. So the range of materials that you regularly find in construction is much more limited. So maybe we want to look at how construction can develop its resilience by learning from some of these other areas. So my research has really been in these areas here, looking at things like weight reduction. So how can you achieve greater mechanical performance from materials? How can you achieve multifunctionality? How can you get materials to do more things without adding extra weight? Also defence, so high performance materials. How do you protect structures by combining materials in complex ways? And what I'm interested in really is how can this understanding really reinforce or help to promote resilience in construction? And I can see two areas that might benefit from this. So one is trying to reduce energy dependency in construction. So here we're interested in reducing material usage for saving weight, for saving fuel. But the production of construction materials it constitutes a significant proportion of energy demand around the world. So if we can reduce the amount of material that we use, there's a potential there to reduce energy dependency in construction. But also consumption in use. So when buildings and infrastructure are being used, if you can reduce the amount of energy that they require, that can help with this issue. And secondly, is something that Paul touched on earlier on, is this issue of resilience against extreme loads. So things like natural hazards, so extreme weather events, and also malevolent action, terrorist attack. So can things that we've learned from defence be propagated in this area? So I'm going to give some examples, starting with this energy dependency issue. So, as I mentioned, what we're interested in is whether we can learn about using materials more efficiently. And this is something that there's been a lot of research in Cambridge looking at this for other applications, in how we can develop materials which work better. So this shows a sort of a property map. So we've got material strength here and material density. And where we want to be is up here. So we want materials that have a high mechanical strength, but have a very low density. So they're very efficient materials up here. So traditional construction materials sit up in this corner here. High strength but high density. And we can alter the properties of materials by changing their topology and changing their constituent materials. So an example is foam, so very lightweight materials, but they sit in this corner, so they get us no closer to the target zone. They've got low density but very low strength. We can improve things perhaps by using metallic foams. There's been a lot of research in Cambridge on the mechanics of these types of materials. So by foaming aluminium, for example, and that pushes you sort of in this direction. So we've got a bit higher strength but a bit higher density. But more recent research has focused on materials like this. So these are lattice materials. So these are structured materials. So you're distributing your material in a very efficient way, and that starts to make progress in moving the materials in the right direction. So how can we sort of learn from some of these examples and apply them to the construction world? So this is really an open question at the moment. And another area of interest to me at the moment is how can you affect energy usage during the operation phase, as well as in the embodied energy in the material itself. So how can you make, for example, buildings more thermally efficient? So I've got a PhD student working at the moment on this material called aerogel. So this is a ceramic foam, a silica foam, but with nanoscale porosity. And this is an image that's been widely reproduced, which shows that this material has amongst the best known thermal properties of any material. And it's starting to find some practical applications, but it has severe limitations. Its mechanical properties are very poor, and it's also extremely expensive. So what materials research needs to do is to look at how we can tackle these two problems of durability and cost. And so these are things that we're working on right now. So for example, building on some of the research I mentioned a moment ago on these high-performance lattice structures, what the student is working on is how we can embed this material within those structures to give you a hybrid solution which is both durable and has extremely good thermal properties. But then we have to tackle the issue of cost. So we're trying to look at ways that we can make these things more cheaply, otherwise they will never be used. So the other issue I want to touch on briefly is this issue of resilience against extreme loads. So this is thinking about when structures experience loads which are either outside of or right at the edge of their design envelope. And there's quite a wide range of different scenarios that could subject buildings and other infrastructure projects to these types of loads. So natural events, so earthquakes, natural disasters, industrial accidents, we've got military conflict, and down here malevolent action and terrorism. And you can sort of broadly categorise these into things that you sort of know what to expect. So natural events, you might have a good idea about the range of earthquake intensity you might expect. Down here things are more complicated because human intervention comes into play to make the threat even more uncertain. And so to some extent these are perhaps more complicated to solve. And they're important issues because there's a lot of money going into this. So the US government spends about $100 billion a year tackling this problem here, Homeland Security. And the reasons for it is because of the potential consequences of these kind of extreme loads, attacks on buildings. So if we look at the terrorism problem, people are worried about the economic impact of terrorist attacks. So if buildings are blown up, that has an effect on investment, internal investment, external investment. People will stop building things if they're at risk. The urban economy is disproportionately affected, and this has a big effect on the developing world where there's growing urbanisation. Foreign trade and tourism are impacted. So there's a big list of economic impacts that can come from such attacks, but also the risk of sort of cascading effects. So spatial effects, so if a building is blown up, what's the effect on the immediate vicinity, but also functional effects. So if you destroy utilities, power, water supply, that can have a big propagating effect on other systems. So this is what's motivating investment in these areas, but that investment comes at a price. So if the government's spending $100 billion per year on terrorist protection, then it's not spending that money on other things, and things like natural hazard mitigation. And so there's an argument to be had as to whether that money's been spent well. So what research can do is to try and make sure that although the reasons for this investment are well understood, can we get the most out of it? So can we improve the performance of materials to make buildings more resilient so that we get more benefit from every dollar spent? And can we sort of try and get secondary benefits from that investment? Can we come up with technologies which might be funded from concerns over this type of attack, but might have added benefits in other types of threats, such as natural disasters? So I'll just whip through some very quick examples. So we're looking at novel types of materials that have multifunctionality. So these are impact-resistant materials that have both a structural function and an energy-absorbing function. So this is a stack of origami material where by changing the fold patterns of our layers, we can change the characteristics, the crushing characteristics of that material. So it's a good example of a multifunctional material. So can we deploy this type of thing in structural applications? Here's another example of novel materials research that's exploiting new manufacturing techniques. So there's a lot of interest in the moment in additive manufacturing and 3D printing. And so what this enables you to do is to create new types of structures that have new functionality. So I've got a PhD student working on these metallic 3D printed structures from the perspective of structural low carrying capacity and energy absorption. And because we can make any shape we like, just as easily as any other, using additive manufacturing, we can sort of parameterize the geometry of these systems, and we can make this, and we can make that, and we can make that, just as easily as each other. And that gives us an opportunity to try and optimize materials for complex situations. So is there scope for this kind of technology to have some impact in the construction sector in terms of mitigating against some of these extreme loads? Here's another example of research looking that, again, was spawned from defence concerns, but might have knock-on effects on other infrastructure issues. So this is looking at how to retrofit structures to protect them from the effects of a bomb blast. So there's the issues of the structure fragmenting. So the particular solution of interest was these spray application polymer coatings, and these were produced by an industrial collaborator called Linex. And they developed these coatings to try and protect buildings from the effects of a blast, to stop it falling apart. But also when a structure is hit by a blast, it can spall, and fragments can get thrown out from the structure, which can cause severe injury. So there's interest in using these coatings to protect against that kind of spall damage. But could this technology have secondary benefits for other threats? So could this be used to protect buildings against earthquakes, as well as against bomb attacks, terrorist attacks? So then we can get knock-on benefits from, the money, the investment might come from protecting things against a terrorist attack, but maybe that's quite unlikely. But maybe we can really get the benefit from these sort of secondary benefits. And really, as we said right at the beginning, we're looking at new ways of bringing research which sits in this domain into these interface areas. So I've mentioned a range of different advanced material solutions, but we need to think about performance cost trade-offs if they're ever going to be used. We need to think about the wider financial considerations for using these materials. So they might be rather expensive, but what do they do to the cost of securing finance for your infrastructure project or the insurability of your infrastructure project? Maybe the net benefit is positive. But also looking at some of the crossovers that move it towards the policy direction. So what are the wider economic and societal consequences of protecting your buildings against extreme loads? Maybe it's not purely financial. But when it comes to government investment, can this technology be used to make sure that the money is being used as efficiently as possible? So we're trying to move this into these overlap areas. And the sort of last slide really is to look at one other area of engineering technology that can benefit potentially this issue of resilient infrastructure, which is looking at new design methods. So I mentioned that advanced materials in construction are perhaps lagging behind aerospace, automotive. That's true also of design methods, but it's starting to change. So there's a growth in these virtual design tools, something known as building information modeling, whereby you design the building in a virtual environment, including a wide range of different aspects of building information, including architectural layouts, structural details, how the thing is put together, over what period of time, and also financial aspects. So can we sort of latch on to this emerging technology, which is becoming a standard in many infrastructure projects, and can we use it and exploit it to try and tackle some of these resilience issues? So at the moment, there's no BIM methodology that looks at resilience, and so this is something that we want to try and address, is whether we can use these techniques to try and help make progress in the resilience issue. And the building information modelling can help you understand the costs of some of the mitigation solutions that I mentioned earlier on. So we need to think about what would be the cost of so here we've got the impact of something bad happening. This could be a natural disaster or a terrorist attack, and this is the cost up here. So what's the cost of the attack on the building, and what would be the cost of mitigating against that threat? And so for fairly modest threats, then you can easily see that you can prevent a big financial cost of impact for a fairly limited investment. But as threats get large, the cost of trying to mitigate against them might become prohibitive. So at some point, you need to accept that you might not fully get back what you invest in mitigating against the risk, but then you have to understand whether there are other knock-on effects that might make that worthwhile. And the main role of the design methods is to sort of help change this picture. So by designing more efficiently, can you change the slope of that curve? So if you can make the cost of resilience lower, then you can push this point further out so that you can encompass a wider range of threats without having to worry about whether you're utilising your investment. And also, you're able to model these trade-offs, these financial trade-offs more accurately using some of these design methods. And one case, just to finish, is the Fukushima disaster, which is an example of a fairly low probability but very high impact event taking place. Something that's highly unlikely to happen, but has major consequences. And so you can see the effect of the consequences of the Fukushima disaster. So having insufficient resilience against this effect has a local effect on one hand, in that it damages the nuclear power plant, but it has a very wide-scale effect in terms of the subsequent nuclear contamination. And so trying to understand, what was the decision right in terms of how resilient that was? How could it be done better? So that's what we want to look at. So to conclude, so we've given you a bit of an overview of what we're interested in terms of looking at infrastructure, finance, risk and resilience. And Paul's given you a financial perspective, and I'll give you a bit of a technological perspective. And we need to conclude what we think, to move this forward, we need to try and engage with a wide community. So we need to try and engage with people in the financial world, the policy world, academics at home and also academics overseas. We need to try and broaden the community with which we engage over these issues to try and make some impact going forward. So thank you very much for your attention.
Can I ask a question? You've, in a sense, been modelling and picking various things that are important. The trouble with that is that unless you have some experimental input to know whether your model and your solutions are any good,
Yeah,
it's not a very fruitful cycle to go through.
that's right. And
So how do you get your experiment? Do you look at Fukushima and say, well, Japan was picked up and moved 3 feet towards China or something?
Well, that's a good point, because
And it sank, and so the seawalls dropped 3 feet and the tide came back.
I mean, modelling these situations is very difficult. I mean, what we can do, and also, you know, and trying to validate these models on that scale is very hard. I mean, we can do things on a local level. We do this regularly in the lab. We look at how materials behave. But some of these really big problems, that is a real challenge. And how do you bridge the length scale of time
Just the opposite.
from small scale things which we can model and we can validate in the lab to some of these, but not just Fukushima, but what about, you know, the wider Japanese and global economy and the knock-on effects of all of that?
Oh, yes, no, I mean, that's...
And I think that's an open research question, is how, you know, how do you go about, well, with the modelling, but as you're asking about the validation of the models and how to, I mean, what we don't want to do is you don't want to, well, I guess there's no opportunity to stimulate another Fukushima just to see what happens with a slightly different scenario, but I mean, I don't know what
Well, you can compare it with Chernobyl, I suppose.
Well, yeah, I mean, it's
So you've got 2 experimental data points.
Yeah.
They're very different.
It's looking at the probability of an event. You know, the Japanese, the designers, they looked at the probability of that happening and decided no, it's not going to occur. The knock-on impact of that is that all new nuclear power stations are having their seawalls put up by another 4 or 5 metres. That's a huge amount of concrete, huge amount of steel, and so we just need to look at it from the risk perspective, but actually from the design side. You know, if some of the materials that Graham was talking about could be utilised, we would use less concrete, which takes up 1% of the world's energy to grind. We could have stuff that's more deployable, and we wouldn't have to go back and redesign, re-engineer some of the infrastructure we put into place. So it's
So there's a cost benefit for
but
that.
it's a low cost solution, you know, because the where the infrastructure is needed needs to be low cost and relatively simple to use. And what we're doing is just at the moment we're just applying very high cost, high energy consumption, sort of a design factor of 5 just to make sure, just to be on the safe side.
Just to be on the safe side.
And you know, this is learning from other engineering disciplines. You know, construction is trying to, however difficult, trying to get back towards a proper engineering discipline and being a little bit more deploying a little bit more science and a bit less sort of just trying to do things by 5.
Well, the issue of maintenance, which was implied in some of the things we put. America's a great first cost country. We build things and then we don't maintain them until they collapse. I mean, to 0th order at any rate.
And that's one issue with new materials. Another issue with new materials is how do you embed them in a design process, which is, you know, the expertise in the construction sector is all tailored towards certain material classes. If you try and throw new materials into the mix, are you going to be sure that you're designing well? You know, is there a chance that you're putting more risk in because people don't know how to model these materials, how they behave, how to design them, how to build them? So you have to be aware of some sort of secondary, potentially negative consequences.
Then you've got a lot of
innovation.
political stuff to get around because there are requirements for how you build a building.
There's vested interest,
And,
which
well, it's just tradition.
I know,
But if you come in with your new materials, you want to get away from that. And then there's a political issue involved. Okay. I'm sorry, I do shut up sometimes. Not very often.
Question for Paul, or really a suggestion on how to sell these projects to governments. So you're very worried, and they seem to be very worried about the risk that the project will get started and won't complete.
less governments, more private are concerned about that. But I mean, governments have got the ability to just put their hand into our pockets and make sure it happens. Now, there's an issue. There's an issue again within the Treasury that are we getting value for money?
I was going to suggest that you could bring to their attention the giant risk of having a lot of infrastructure that's just on the edge of collapse.
Yeah, absolutely. Yeah.
I feel like that should be weighing on the other side.
Yeah, I know, and it's very rarely put together. We've just had an announcement in the UK that we're going to spend 366 billion on infrastructure, of which only 70 billion is government funded. The rest is either private or it's public. Private, public mix or private. But again, it's they didn't say it's because a lot of the stuff's just about on the edge of collapsing, so that's why we need to spend this money. It's more about, hey, look at me, I'm a politician, I'm going to build this fantastic new high-speed railway, I'm going to do this. Again, I've never seen economics of what happens if you just let it go for another 5 years. The US, as much as I love it, some of the infrastructure is a bit just about on there. I mean, there's a lot of bridges I wouldn't want to drive across. But so yeah, it doesn't come up. I've not seen it.
I have a question for Graham, but please put me at the end of it here.
Right.
So I wanted to ask a question on construction and finance. So we've thought about kind of catastrophic risks like attacks, but I feel like one of the most fundamental risks is pretty mundane with construction. It's if I give you this money, will I get what you told me you'll give me? So really the fear is overruns. And so in other contracting industries where there's risk of overrun, say software or legal services, things have moved to a deliverable-based pricing where you give us this deliverable for the price we gave you. And so essentially the purchasers have forced the contractors to assume some of that risk. Now, is that possible in construction? Or?
Yeah, no, it is. It is, and if you look at the worst overruns in any projects or IT, I mean by zillions, yet they never seem to come in for quite the same scrutiny because they're sort of all around us. You actually see them. You don't actually see the big lump of concrete that didn't work. No, it is moving towards that, and projects in construction, most big government infrastructure projects now usually come in on time and on budget. That's because there's been this change within the construction technology, and also things like BIM are really, really helping. So, if you I don't know how many of you guys come from that sort of background, but in the past you'd have your 2D drawings, and the electrical and mechanical guys would sit there, and the environmental guys would sit there. You'd sort of look at your drawings. With BIM, it really helps in what's called clash detection. So you virtually build this building, and the pipes, someone's put a hole over there, and they haven't put the hole in the right place. And you see it, you say, oh, right, we'll solve that now. 15%, 20% reduced costs and time. So it's going to be much easier for contractors to say, I know it's going to cost this amount. This is a fixed tender price. I haven't talked much about tenders because tenders vary around the world, and it's quite complicated and it involves a lot of other issues. But it's a major factor.
But it speaks to the point of that, how a market is structured, how the labor market for construction is structured matters.
Yes. But also, I mean, again, we could get onto many other issues of societal problems, but there will be less people on construction sites. A lot of it will be off-site manufacture, so the days of lots of guys in hard hats walking around will be less and less and less.
But this also gives the prospect for introducing some new materials concepts. So if you have off-site manufacture, then there's more prospect for innovation in material. So I think there's other positives from that.
We've been talking. By the way, it's great when you see the same citations in your slides as in ours. It's like, oh, okay, there is something else out there. So we've been talking about this for a year and a half, and it seems to be three central problems. And I kept hearing this, but I just wanted to see if you would agree. One, that we've got inadequate feature discount ratios.
Yep.
That's a big one. The second one is that we have optimization schemes that prize efficiency over fragility. And I'm not an engineer, but it seems to me there is a point where you do start paying in fragility for every increase in efficiency and dependence. But all our tools are about being at that optimal, just that one last little point on the curve, which might be very efficient, but very dangerous.
Yeah.
And the third one is, and Fukushima is a perfect example of that. You could have made that map so the reactor floods, this part of Japan gets radioactive, this part, the problem is that the only one who's actually paying for Fukushima is Tokyo Electric. And Tokyo Electric doesn't really give a damn if Nissan doesn't get its widget delivered because Fukushima plant had to close down. So you've got a problem of discount ratios, you've got a problem of optimization, and you've got a problem of collective goods.
It's a big algorithm somewhere, and it's a problem. I mean, the discount ratio site, we have, capital is taking far more reverence than it should. We're paying far more attention to the financial scarce resource than the things it's building. That's a wider issue, and yeah, you're absolutely right. But we have to come up with, we're not trying. We'd love to be able to solve all the problems of the world, but what we're trying to do here is just say having that common language to reduce that discounted price, so that everything's just a little bit cheaper. Is one step in the right direction. The issues of fragility, I think interdependency. Robert Mayer's group at Cambridge, they're some really smart guys developing these things, and I'm a mechanical engineer, not an electrical engineer or electronic engineer. The electronic engineers like to work at that 0.5%, that last bit, to squeeze it in, and then it breaks.
But I think that, the improvements in design methods are really going to help that second point. So if you've got better design tools, then you know where that sort of crossover point is, where you're
where the real optimization.
Where actually you're at risk in your operating envelope. There's a chance that you're at the point of being close to failure, or there's a wider range of possible scenarios that could cause failure. So I think it's not so much whether new technology moves that point; it's knowing where that point is and making sure that that's outside of your operating window. So I think better design tools will reduce conservatism in construction. So it will allow you to get closer to that point with confidence. And I think that's going to happen.
Yeah, I think if you look at automotive design, automotive supply chains, automotive design in itself, when I had my first car, 45% chance it would break down. The last few cars I've had, nothing ever happens, because they have engineered it to that very point. So it can work.
Except the car that you're driving now is, in a sense, more, as I understand it, again, there's more engineers here who can tell me, does have a greater probability of a catastrophic failure. I mean, I've always thought I'd rather have a Lamborghini than a Volkswagen Beetle from 1966. However, if I was crossing the desert and all I had to fix my car was a stick and some tape, I'll take the Volkswagen.
Yeah.
So you're paying for that you're paying for that. We've reduced the variance on the failure of these cars, so you don't have to worry. But if they do fail, if the electrical system goes out,
well,
you're screwed.
You open the bonnet, you've got to even get into it. But I've had German cars. They tend not to do that, but yeah, they can. I agree, but there's always a trade-off. There's always a trade-off somewhere. Difficult when you're building these big systems that so many people are dependent upon.
But, aero engines are getting more and more complicated. They're becoming more and more efficient. So it's probably better in the long run, I think, to go down that road.
So I have a question about working at that intersection. So in the beginning of your presentation, you said how important that is. That's where the biggest challenges are, and that's where the biggest outputs. This is where you have to make the greatest impact. But what does that look like, and how does that happen? I'm an engineer and civil engineer. If you look around, actually, half of your audience are civil engineers. So we're working towards better bridges and buildings, and for extreme events, and for just wear and tear. What does that look like? Do the both of you work together on the same projects and share students? How do we, and maybe this is a question for Miguel, how do we as civil engineers find that person to work with to kind of make the next step in advancing the work that we do to have the public policy or whatever implemented?
Yeah, absolutely. I mean, we've got a reasonably nice website now, so it makes it look. I mean, Graham showed a huge building there, but we only started this in April. So we're sort of, one of the things is going out there and saying to people, what do you think we could do? What can we do together? What's the challenge? I spoke earlier about that it's all a bit nebulous at the moment, and we need some little gravitational points to all start sort of fixing and circling around. We're working with the Langer Rourke Centre, and they're a big UK global construction company, and they're looking at civil engineering technologies, and they're also interested in the financing side. So that's how we started this, because they don't get to build their bridges unless the money comes in. So that's how we're slowly sort of piecing things together. But we don't quite have an answer.
No, I mean we're still testing the water. I mean issues like project funding. So the Engineering and Physical Sciences Research Council, with a project where we want to fund 2 engineers and 2 economists, we haven't yet tested the water as to how they'll respond to that, because the Research Councils are always saying they're very much in favour of multidisciplinary research, but I'm pretty sure they'll also be pretty tight on making sure that they only fund their discipline. They want the Economic and Social Research Council to fund the economists. So I think it's something that there's not been a lot in this area happening in engineering so far. I mean, engineering projects have been all engineers. Economists have worked on their own, and so we're really testing the water as how we can have projects that fund both groups on one project, and we'll let you know how that pans out.
We're putting in for $1 million grant, which we think we've got a good chance to get, but we've done that. As Graham said, it's like multidisciplinary is what we're looking for until you actually offer it to them. They go, we don't want that, no economists involved.
So we're not encouraged to submit it yet.
Yeah, we haven't quite done it. We're slowly getting there. We're trying to refine it, and also just test to see if it's going to reject it. It's also why there's been a lack of academic research on it, because everyone sits in their little silo. In the business school across the road, everyone's doing fantastic quantitative research, but they're mostly doing it on derivatives and the finance side. The engineers are doing their own thing. No one's talking to each other.
Let me ask a question that perhaps doesn't quite share the frame that you put around this set of issues. What is it exactly you're trying to make resilient? So let me explain in the sense that building, a city sewage system or train system or whatever it is you might want to, or buildings, or that's a thing. And so you can imagine ways of doing that. But one of the things that I think is of related interest is that we're actually talking about the resilience of, as you mentioned, societies and the ecosystems within which they're embedded, given where we are today in the world and going forward. And an argument could be made that finding ways to make large infrastructure projects go further faster, more efficiently, in all the ways that you described, actually may undermine the resilience of the system as a whole. Because much of the understanding that, from the other side, that seems to be emerging is that a lot of actual resilience in real crisis situations emerges out of local capacities, and that actually distance is a profound source of resilience. Not being connected, but being able to navigate that connection from where you are, from ground zero, is actually a fundamental source of resilience. And so I can imagine a critique that goes, in one sense, echoing Mahatma Gandhi's critique of the British railway system, that all they do is spread disease and sin. He was right to some extent. You could argue that this actually could end up making the existing problem of larger resilience worse, not better.
That's right, and we can enter a philosophical debate on that as well. What I'm trying to do is to get the parts of the world that I've spent a lot of my career in actually building structures that make people's lives as comfortable as ours are here. And so my goal is to get that huge amount of money that's sloshing around the world into something that enables people to live a life of fulfillment and dignity and expansion. There are other implications beyond that, and I agree. But we're tackling this from an engineering and a finance perspective at this beginning. I'd like to answer some of those questions, but maybe come back in a couple of years.
But may I just kind of,
Yeah.
because I'm not sure it's just an ethical, I mean, there's obviously an ethical component of this, but I think there's a design component.
Yes, no, there is. Yeah.
Which is where, and again, this is making it far too linear, and the problem is that it's non-linear, is putting it into your design component. What are the effects for a web if this thing goes down, or designing always having a reserve, or whatever it might be, where you give up. For example, it makes absolutely no sense for some of these countries to be growing their own food in terms of pure economies of scale.
Yeah.
But you can put into the design, but it's not a bad idea to keep 10 very inefficient farmers around, or whatever it might be. Can you see a way of putting that into the design so you can keep a little possible autarky if needed?
But let me just add to that, because you mentioned Fukushima, which is fascinating, because some of us here have been thinking about this for a while, about nuclear reactor safety issues. So the earthquake and the tsunami that hit there, the Japanese had said that they had looked at the historical record going back 300 years, and their reactor siting and design and protection was good for that. It turned out that 1,000 years ago, there was an earthquake and a
Yes.
tsunami that flooded exactly the same area.
Yeah.
Right? Now the problem was that for some Japanese nuclear company design engineer thinking, really you want me to design something that might deal with a once in 1,000 year event?
Yeah.
Right?
Yeah.
The consequence, of course, is that, given what's happened, it might not have been a bad idea to think
Yes.
about it.
Yes. Exactly.
So, as Miguel says, there are multiple levels at which when you start thinking about what you should build into your design, they actually end up being at cross purposes.
Yeah, how much resilience do you want to build in? What's worth investing in?
Yeah, which we're trying to show on that graph. There's a point, and sorry, Graham, I've seen a paper that the US government invested in some academic research after 9/11, and it was something like $6 trillion to make every single major US city secure against it. So in the end, they said, well, maybe it's just Washington and New York, especially Washington, that we should look after. Las Vegas, Chicago, you're on your own. And it's how do you get that decision making, and what parameters go into that decision making? The other area we're trying to get is not just accounting at the moment. So the UK Treasury, we're just using standard accounting methodology. We're not looking into the future and saying, well, what's the impact of not investing in that or over-investing? And that really is a lifetime challenge for me. I've not seen any methodology that scopes that out yet. The parameters you're discussing. But
again, another very interesting conversation. And picking up on those two questions over there, I'm actually, just to humor it up a little bit, reminded of the good old Soviet Union. Because in those days, they used to have, they would spend time on a project, and then they would approve the project and appoint a project manager.
yeah,
And then there would be nothing but execution,
yeah.
either the project or the project manager. So, coming from that thought, picking up on this, I think that's a big point, because the era of the big dams is over.
Yeah.
They served a purpose of selling a huge turbine that was made somewhere else that would never be supported indigenously, locally, or however you want to call it. And so that one huge dam that you would build for the same cost that it was dislocating population, destroying ecosystem, et cetera, all those things that go with it, you could build 100 damlets and produce perhaps better infrastructure that could serve the local population far better. But where I want to go with that is one of your slides that you had with the grid in there, you had a group of countries, different regions. And I couldn't help but notice that the number one that you had marked, number one, with Canada, Australia, and New Zealand. The two other countries in there were the total big brother countries, Singapore and China. So is this the model that you're talking about? Is really suited for a big brother, a top-down operation? I mean, is this China's model of central planning really winning in here?
Well, I'm not an economic historian, and I think China has taken that sort of industrialization that the Soviet Union attempted in the 20s and 30s at huge cost, at huge human cost. And I'm not saying,
mistakes.
yeah. and I'm not saying China has done it without that, but it seems to have achieved it with this sort of hybrid economy that it's got. You know, I have my own business as well, and I'm looking at a project in the Middle East. I'm going to be using Chinese contracting businesses, and they're a hybrid between they've got state investment in them, but they're private at the same time, but they have to go look for business around the world. And it's a model that works for China. You know, I've had these discussions with the Chinese. You know, why? You know, how can you have this economy yet still have this quite dictatorial political system? And the answer I've got back on 2 or 3 occasions is, well, we're scared of not having it because China's been in chaos for so many decades prior, so that's why we have this. It works for some countries. I mean, Singapore is not the bastion of democracy. It works in Singapore, but you know, you look at Australia. Australian infrastructure is extremely good, and that's much more free market based. I don't think there's one model that works globally. All I was pointing out is that some countries have a sort of connected issue of infrastructure. You think about, you know, I first started going to China in the early 90s. You think about what China looks like now, and I remember it back then in terms of people's standard of living. Now, the impact on that for the local ecology, for the non-material standard of living is you know, up for debate. It works for them at the moment, but I you know, maybe not in the future. So.
Well, thank you so much. That was great.